All right, let's get started. So first of all, welcome to CEE305. So this class is called Applied Probability and Statistics. Okay. Introduce myself. My name is Lin Shen. I'm an associate professor from a civil engineering department. My office is Holmes House 344. So my phone number, and this is my cell phone number. I put it in the syllabus. Email. So the class hours, 2 p.m. to 3:15, Tuesdays and Thursdays. Okay. So for the first 2 weeks, as we all know, we will be online class. Okay. So use this Zoom link. I don't know when, probably after the first 2 weeks, we'll go back to our formal classroom, which is in Kukendall Hall 209. So Kukendall Hall 209. So I will let you know before we start the in-person teaching. All right. So if office hour, I think for this semester, if you want to meet with me, let's first try to set up a Zoom meeting. Okay. All right. Then for the textbook for this class is Statistics for Engineers and Scientists. Okay, so you need to purchase the so-called Connect code. Okay, I upload the instruction how to get started Connect, from Lolima into the Connect website. Okay. So as you can see from the instruction here, so this is what I got from the publisher. So they have the textbook and also the website. Okay, so this is a detailed instruction how to pair a Connect account with Lolima. Okay, I think you can have a discount by doing this way. Okay, so you need to log in. Find my H campus. This is the link for the publisher's website. Okay, so this is the publisher website. You need to connect. Okay, so connect our course. Okay, so this is just an example. And you need to log in account and create a new account. If you have an existing account, you may just log in. Okay, and go from there. Okay, so let me know if you have any problems getting connected with the website. So this is very important. You do not need to purchase the hard copy of the textbook. So everything will be on the Connect website, including the textbook. Okay, and also all our homework, quiz, midterm, and also the final exam will come in from the Connect website. Okay, so for your final grade, it will comprise homework. You have around 4 to 5 homeworks. Okay, so the homework around 25% of your final grade. We have around 1 or 2 quiz, 5% for quiz. We have 1 midterm, 30%, and 1 final exam, 40%. Okay, so the midterm will occurs after we finish chapter 4. And the final exam will be comprehensive, which means final exam will cover everything from the beginning to the end. Okay. So the topics covered in this class. So chapter 1, the first 2 weeks, we talk about how to get a sample and what is descriptive statistics, what is mean value, median, standard deviation, and so on. And then chapter 2 is called probability. So we'll discuss what is random variables, what is permutation, for example, how to use counting method to calculate the probability, and what is conditional probability and independence. Okay. So chapter 2, we use around 3 weeks also. Okay. Then chapter 3 is a short chapter. It's called propagation of error. Okay. Chapter 4 is one of the major focus. It is called commonly used distribution. We'll discuss the famous normal distribution and also Poisson distribution, binomial, Bernoulli distribution, and so on. So chapter 4, we use around 3 weeks, 3.5 weeks, 3 to 4 weeks. Okay. And after chapter 4, we will have our midterm. Okay. The second half will be chapter 5, chapter 6, and chapter 7. Okay. So chapter 5 is called the confidence interval. Okay. Depending on different scenario, we calculate the so-called confidence intervals. Chapter 6 is called hypothesis testing. Again, similar to chapter 5, for different situation, we do the so-called hypothesis testing. Okay. So these 2 chapters is take about 5-6 weeks in total. And the final chapter will be chapter 7. It's again very short. Similar to chapter 7 is called correlation and simple linear regression. So this class will cover these 7 chapters from our textbook. Okay. And here is the student's view. You will see from the Connect website after you create the account and log in. Okay. So before we start, as I always do for my classes, let's introduce ourselves. Okay, so that's a good way to spend about 20-15 minutes to introduce to each other, especially when we do this online teaching. I don't know for how long. So starting from me, again, my name is Lin Shen. I have been with UH since 2011, so almost 11 years. My research focus on cement and concrete, so about construction materials. Okay, for example, how to design sustainable concrete using waste materials such as coal ash. Okay, so my office is Holmes House 344. So yeah, let me know if you have any questions. All right, so that's about me. Then could you also introduce yourself? Okay, so let me just read your name from the screen. So the first one I see is Steve. Hi, Steve. Would you introduce yourself?
Hi, yeah, it's nice to meet everyone. My name's Steve Wilhelm. I just started a graduate degree at the Ocean and Resources Engineering Department. I did my undergrad at the University of Miami, and I was in the military up until recently. I was a Navy diver. So I'm sort of covering down on a few engineering deficits, which is why I'm taking this course. And yeah, that's mostly what I'm about.
Great. So since you are graduate students, who's your advisor? Oceana?
No, it's starts with an F. I have to write it down.
Okay.
But it's general. I haven't chosen a
okay.
research interest yet. Yeah.
Okay, so you just started. Okay.
Yeah, just started.
Yeah.
It's my first semester. Yeah.
Great. Okay, nice to meet you. Thank you, Steve. Next, I can see is Hannah Asano. Could you introduce yourself?
Hello, everybody. My name is Hannah Asano. I am a sophomore at the UAE Manoa, and I'm majoring in civil engineering and the island of Oahu.
Okay. Great. Nice to meet you. All right. Danny, do you have a microphone to talk? Right.
Hi, my name is Danny. I'm a civil engineering major. I'm a junior, I think, this year. I'm not sure. I'm on my fourth year now, so I lost track. Yeah, that's about it.
Okay, thank you, Danny. Janelle Cabra.
Hi, I'm Janelle Cabral. I am a junior, actually, and I am majoring in civil engineering.
Okay, thank you. Derek?
Yeah, hi, my name's Derek Yamane. I just graduated from University of Oregon with a environmental science degree, so I'm back at UH trying to get a environmental engineering degree now, so
Oh, nice.
I'm back in school.
Okay, welcome back. Jonan Masura.
Hi, I'm Jonah. I'm a sophomore this year and I'm from the Big Island.
Okay, Big Island. So Rick Karashima.
Hi, I'm Rick. I'm a civil engineer major, sophomore, and I live on the on Oahu.
Okay. All right. So Darren Nekoba. Sorry.
Oh, hello, my name is Darren Nikoba. I'm a civil engineering major from the Big Island.
Okay, Darren. Jacob.
Hello, my name is Jacob Maritani. I'm an electrical engineering senior, and one of my hobbies is I like to play tennis.
Okay, me too.
Oh,
yeah. All right. Thank you, Jacob. And who else? Isabel Lassen.
Hi, I'm Isabel. I'm originally from Oregon and I'm a sophomore in the civil engineering program.
Okay, Oregon. Rainy Tangona.
I think that's me. Hi, my name is Rianne. I'm a sophomore and I'm a civil engineering major and I'm from Oahu.
Okay. Jayment Yadav.
Hi, my name is Jamin. I'm a senior in civil engineering.
Okay, Jayment. So Kun Shu.
Hi, my name is Kun Shu, sophomore from Oahu, majoring in civil engineering.
Okay, thank you, Shu. Yung Da Shu.
Hi, I'm Seo from South Korea. This is my second year at NOAA. I'm majoring in civil engineering.
Okay, welcome. So Andrea Fernandez.
Hi, my name is Andre. I took a break. I took a 1-year break, joined the Army, and now I'm back.
Okay, welcome back. See next. John Melv.
Hi, I'm John. I'm from the Ocean and Resources Engineering department. I've completed my all my graduate course requirement, but I need to take statistics class, so that's why I'm in this class.
Okay, all right, John. So Kobe Kosaki.
Hi, my name is Kobe. I'm a sophomore and I'm from Hilo.
Hilo, okay. All right. So Ashley Armand?
Hi, I'm Ashley. I'm from California and I'm a junior.
Okay, California. And where else? Irene Madrino?
Hi, my name is Aaron Madrano, and I am a junior studying civil engineering, and I'm from Oahu.
Okay, okay. Gabriel Heckley?
It's Gabriel. Sorry, the spelling's kind
Yeah,
of weird,
sorry,
but
yeah.
I am Gabriel Packleb. I originally reside on Maui. I am a civil engineering major, and I currently reside with family on Oahu.
Okay, all right. So Dan Sung Buyatao?
Oh, sorry, it's Danton Boyaka.
Sorry.
Yes,
Yeah.
it's a weird spelling also.
Ah.
Yeah, I think I'm a junior CE major. Live on Oahu.
Okay, all right. Gavin Kondo?
Hi, my name is Gavin, and I'm a junior studying civil engineering, and I'm from Oahu.
Okay, Gavin. So next is Mark Anthony.
Hi, my name is Mark. I'm from Maui, currently a sophomore studying civil engineering.
Okay, Mark. What else? Matthew Kim.
My name is Matt. I'm a junior at the CE program. Part of the Hawaii Air National Guard, working as an electronics technician.
Okay, great. So Grant C.
My name is Grant Calypso. I'm sophomore and I'm from Kauai.
Okay, all right. So Taylor Kilipio Nauchi.
I'm Taylor. I'm from the Big Island, and after I graduate, I'm going to commission into the Air Force.
Okay, nice. Cyrus Kamalu. Sorry.
Hi, my name is Cyrus. I'm a junior at UH, and my major is construction engineering.
Okay, great. So McKellen Michelle.
Hello.
Yeah,
okay. Sorry. I'm McKellen. I'm from Maui. I'm in civil engineering.
Okay, from Maui. So Karin Urasaki. I think this is the last one.
Okay, hi, my name is Kylie Urasaki. I am a senior in electrical engineering and I am from Oahu. Very nice. Thank you.
Okay, thank you. So did I miss anybody? If anybody hasn't introduced yourself, please do so. Okay, so this is our first class. So today we have how many? We have 30. Okay, so totally we have 32 around. Okay, good. So let's get started. So chapter 1. So chapter 1 is called sampling and descriptive statistics. Okay, so we'll introduce the very basic idea why we should study statistics. What is statistics? Okay. So statistics dealing with uncertainty in repeated scientific measurement. Okay. And we also trying to draw conclusion from a sample or called data. Okay. So the conclusion should be as reliable as possible. It will also help us design experiment and based on the result of the experiment, draw reliable conclusion from it. Okay. So as an engineer, we use statistics all the time. Also, statistics will be helpful to be a well-informed member of society. Just give you an example for social politics. Everybody have heard about, for example, the approval rate for president, or help us explain economic trend. For example, what is the current unemployment rate. Okay, for example, 4%. So how we get this 4% unemployment rate? So we use in the knowledge from statistics and do a certain experiment. For example, make a bunch of phone calls. Okay. So here is an example. Let's say we have a machine that will make steel rod. Okay. So the steel rod will be used in optical storage devices. Okay, whatever. So the specs for the steel rod diameter is this. So 0.45 plus minus 0.02 centimeter. Okay, so within this range, so we see the steel rod diameter meet the specs. Outside, it is not meet specs. Let's say we have 1,000 rod made by the machine, and engineer want to know how many of these 1,000 rod meet the specs. Okay. But it is very, very time consuming to measure the diameter of this 1,000 rod. So what he do is he draw a so-called random sample, or simple random sample of only 50 rod from this 1,000 rod. He measured the diameter of this 50 rod. He found that 46 of this 50 rod, or 92% of the 50 rod, meet the specs. So 0.45 plus minus 0.02 centimeter. Okay. So it is unlikely that the sample of 50 rod will perfectly represent the whole population, which is 1,000 rod in this example perfectly. Okay, but it will be pretty close to 92%. So the engineer may try to answer questions such as this. So how large is the typical difference for this kind of sample? Okay. So this is the difference between the sample proportion, which is 92%, and the population proportion, which is what is the percent of the whole 1,000 rod meet the spec. So we're gonna be able to answer this question after chapter 1 and chapter 2. Also, what interval give a good estimate of the percentage of acceptable rod in the whole population, which is 1,000 rod, with a reasonable certainty. Okay, so we will learn so-called confidence interval from chapter 5, and we'll give the answer for this type of question. So another possible question is, how certain can an engineer be that at least 90% of the rod are good? So he get a sample of 50 rod, and he found out 92% of the 50 rod are good. But how certain can he be that at least 90% of the 1,000 rod are good? So this is the question we can answer after we study chapter 6, which is hypothesis test. So the knowledge we learn from this class will help us address questions like this. Right. So section 1.1. So here, let's first learn some of the new definition. So the first one, population. So in statistics class, population here is entire collection of objects or outcomes about which information is sought. In the previous example, the whole population is 1,000 rod made by the machine. A sample is a subset of the population. In the previous example, we have a sample of 50 rods. So the sample containing the objects or outcomes that are actually observed. So the engineer take a sample of 50 rods and he actually measured the diameters of these 50 rods. a simple random sample, or SRS, the size is n, is a sample chosen by a method in which each collection of n population item is equally likely to comprise the sample. So just as what we did in a lottery. Okay, so in a lottery, let's say we have 10,000 tickets in a drum. So we rotate a drum and we take 5 draw, we mix it, we take 5 draw 5 tickets. So each of these 10,000 tickets is equally likely to be chosen from the 5 pick. Okay, so we're trying to do that for our sample as much as possible. And we call this sampling method a simple random sample. Okay, so another example. So we have a university and professor trying to find out the average height of students at the university. Okay, so she got a list of all the 50,000 students at the university, and she assigned a number to each student. Okay, so 1 to 50,000 number. Then a random sample, a random generator generate 100 numbers. So that's corresponding to 100 students. Okay. And this is an example of simple random sample. Okay, we can use software such as Excel to choose the random 100 number. Okay, so this is similar to what normally do in a lottery. Okay. This is simple random sample. The opposite of that is called a sample of convenience. Okay, so sample of convenience is a sample that is not drawn by a well-defined random method, like a lottery. Okay, so sometimes we cannot get a simple random sample, so we have to use a sample of convenience. If we do that, we need to consider this. One, convenience sample may differ systematically in some way from the whole population. Okay. As a result, they should only be used when it is not feasible to draw a simple random sample. Okay. And if we have a convenience sample, we should think very carefully. Is there any ways in which the sample might differ systematically from the population? Okay. So for example, the professor wants to know the average height of the 50,000 students in a university. So the best way is to draw a simple random sample of 100 students. If she chooses a sample of convenience, for example, 100 students from College of Engineering, okay, then we should think carefully if the 100 students from College of Engineering will be different from the whole population, which is the 50,000 students of that university. Okay. So let's look at another example. So we have a construction engineer. So he got a shipment of 1,000 concrete blocks, each weight 50 pounds. So very heavy, 1,000 concrete blocks. Okay. The blocks are in a large pile. Okay. Engineer wish to study the crushing strength of the block by measuring the strength in a sample of 10 blocks. So he just take a sample of 10 blocks and measure the crushing strength of that sample. Okay. It may be very difficult to take a SRS, which is a simple random sample. Okay. Because if we do that, we should get blocks from the middle part of the pile, the top part, and also the bottom part of the pile. Remember the concrete blocks is very heavy, 50 pounds for each. So it's not realistic to get a simple random sample. So instead, it just take 10 blocks from the top, which is easy to measure. Okay, so this is an example of a sample of convenience. So a simple random sample is very good, but it's not guaranteed to reflect the population perfectly. So like we get a simple random sample of 50 rod from 1,000 rod, and we measure the diameter, but it's not guaranteed the 50 rod will reflect the whole population perfectly. Okay. And simple random sample always differ in some way from each other. For example, we take one simple random sample of 50 rod, we measure the average diameter, then we take another 50 sample item and we measure diameter. So these two simple random sample will differ to each other. So two different samples from the same population will vary from each other as well. Okay. So we call this phenomenon as sampling variation. Sampling variation. So for the raw sample, in a sample of 50 raw, the engineer found out 92% meet the specs. Okay. So in the population of whole 1,000 rod, it is unlikely that exactly 92% will meet the specs, but close to 92%. But how close? Okay. So because sample variation is more realistic to think that the true population of rod, 1,000 rod, that means the specs will be close to 92%, but not exactly. Then let's look at different type of populations. Okay. Population involving a number of physical objects, okay, such as in the previous example, 50,000 students at a university, 1,000 concrete blocks, okay, all 1,000 steel rods in the first example. Okay. So we call this type of population tangible population. Okay. So this population are always finite. So 50,000 students, 1,000 concrete blocks. So the number are finite. A conceptual population, on the other side, consists of all the values that might possibly have been observed from a population. Okay. So here give us another example. So a geologist with a rock using a very sensitive scale. He measures several times. Each time the scale gives a slightly different reading. Here, the population is conceptual. So the whole population means all the possible reading that the scale could in principle produce. It's not finite, actually in the previous example. So this is called conceptual population. All right. So another definition here is called independence. Okay. So the items in a sample are said to be independent to each other if knowing the value of some of the item does not have to predict the likelihood of the value of others. Okay. So we'll give you an example in a moment. Okay. Here it says item in a simple random sample may be treated as independent in most of the case, but not always. Okay, so that's exception. The exception occurs when the population is finite and the sample comprises more than 5% of the population, which means if the sample size is large enough, more than 5% of the whole population, then different samples cannot be called independent to each other. Okay. So why, the sample size matters? So let's look at this. Let me draw something here. Let's share with you my notes. Okay. Okay, we are on page 14. So let's see, the whole population has 2 A's and 2 B's. Okay, we try to have 2 peaks. So the first peak, we pick one randomly. And the second peak, we pick another item from this whole sample. Okay, so let's see if the first peak we have A. So first peak we get A. Then for the second peak, after first peak we have 1 A left and 2 B left. So for the second peak, the probability we call that PA. So PA here means the probability we pick A in the second peak is how much? It's very straightforward because we have 2B here, 1A here. So the probability we pick A randomly is 1/3, right? And similarly, the probability we pick B for the second peak will be 2/3. If the first peak we get a B instead, okay. So the first peak we get a B. So after first peak we get 2A left and 1B. Okay. Then for the second peak, so what is the probability we get A? Very easy. So right now we have 2A left and 1B. So PA will be 2/3. And the probability we get a B will be 1/3, correct? Okay. So this is an example of dependence. Okay. That means we see the first peak and second peak are not independent to each other because the result for the second peak, PA, will depending on the result from the first peak. If the first peak is A, for the second peak, we get A, the probability is 1/3. If the first peak we get a B, for the second peak we get A is 2/3. So it's not independent to each other. And that is because the whole population is only 4 and the sample is 1. Okay, so the sample size relatively to the whole population is much larger than 5%. If the sample size is so large, let's say we have 2 million A's and then 2 million B's, things will change. Okay, so again, for the first peak, no matter we get A or B, for the second peak, the probability we get A will be very, very close to 50%, right? So, one from these 2 million A's, we still get very close to 2 million. So the chance for the second peak for PA is still close to 50%. And so does PB is also close to 50%. That is because the sample size, which is 1, we pick one item from the first sample, is much, much smaller compared to the size of the whole population, which is 4 million. So we have 2 million A's and 2 million B's. So when the sample size is small enough, then the different sample items, we said they are independent of each other. Go back to the slides. So any questions so far? Okay. So we have other sampling methods other than a simple random sample, which is the best. Okay. So that will include weighted sampling. So what is weighted sampling? So some items has a higher chance to be selected. For example, in a lottery, the chance for each ticket is similar. But if we want to increase the chance we win the lottery, we can buy more tickets. Okay, so if we buy 10 tickets, then we have 10 times more chance to win the lottery. So that's one example of weighted sampling. Stratified random sampling. So that it means for a whole population, we have subcategories. Okay, and we also have a clustering sampling. So just remember, we have different sampling method, but by far the most commonly used sampling method is this simple random sample. So obtaining data, experiment is a process by which observation is obtained. So for example, we try to measure the daily maximum temperature, or we test the strength of concrete, okay, and so on. So that is experiments. For experiments, we have controlled experiments and observational study. Okay. So a controlled experiment is one in which the experimenter can control the value of the factors. Okay. So this is what we normally do in the lab. So I study concrete. We do the controlled experiment in the concrete lab all the time. So the reason we want to use controlled experiment is when design and conduct properly, controlled experiment can produce reliable information, a good correlation about the cause and the effect between two or more vectors. Okay. For example, so this is asphalt concrete cylinder. Okay. So let's say we're trying to measure how strong the asphalt concrete cylinder is. And we can change the temperature of the asphalt cylinder before we test its strength, and then find the correlation between the temperature of the cylinder and the strength of the cylinder. So this is we call the controlled experiment. Okay. Sometimes we cannot have a controlled experiment. Okay. So our observational study is one where the experimenter simply observe the facts, the factor as they are, okay, without having any control over them. Okay. For example, the number of cars arriving in a certain intersection. So that's something we cannot control. We can simply observe or count how many cars in that intersection. or precipitation, how much rain in a certain location, and so on. Okay. So observational studies are not nearly as good as controlled experiments, but sometimes we have to deal with that. Okay, so new definitions. Variables. So variables is defined as a characteristics that changes or vary over time and or for different individuals or objects under consideration. Okay, example. So white blood cell count. So time to fill a light bulb. Okay, how much time until crack appear in a concrete pavement? The strength of the concrete mixture specimen. The crushing strength of the concrete block. So these are the example of variables. And an experimental unit is the individual or objects on which a variable is measured. For example, the concrete block is the experimental units. And the variable we measure on that block is the crushing stress. Okay. So a measurement results when a variable is actually measured on our experimental units. So we get the crushing strength on concrete block. So that's the measurement. A set of measurement, we call that delta. Okay. So delta can be obtained on either a sample or a whole population. Most likely we'll do that on a sample because it's easier. Okay. Another example, the variables is the color of eye. Okay, we have brown, green, and so on. And experimental units will be present. Okay. And typical measurement will include the color of the eye, brown, green, blue, and so on. Another example, this is again a asphalt concrete beam. So the variables in this example will be the number of load repetitions to apply many different cycles of load until the beam fails or the beam cracks. Okay. The experimental units will be the asphalt concrete beam. And typical measurement will be like the concrete beam cracks after 51,000 repetitions. So let's look at delta classifications next. Okay. We can measure one variables on a unit. For example, measure the strength of a concrete block. So if one variable is measured on a single experimental unit, we call that univariate delta. Sometimes we measure two variants, so we call that bivariate delta. So two variables are measured on a single experimental unit. For example, for one concrete blocks, we measure two variables, the strength and also the weight of the block. So two measurements on one block. So we call that bivariate delta. Okay. So more than two, we call that multivariate delta. For delta, we also have two major types, the qualitative and quantitative. Okay. For quantitative, we have discrete and continuous variables. So when a numerical quantity is assigned to each item in the sample, and the resulting set of variables is in numerical, such as how many centimeters in height, how many kilogram in weight, and age in years. Okay, so this is an example of numerical quantitative data. When the sample items are placed into different categories, such as different higher colors, zip code, a different type of asphalt concrete, so we call that categorical or qualitative data. Okay, so two major categories. And under quantitative variables, we have discrete variables, means it can assume only a finite or countable number of values. For example, the strength of the concrete blocks. Okay, we can measure the strength of 10 concrete blocks, 50. So this is discrete variables. Continuous variables, it can assume the infinitely many values corresponding to the point on a line intervals. Okay. For example, we use a thermometer to measure the temperature of the room. Okay. So what we do is, we take many readings, and we can plot a curve. So the x-axis is the time, the y-axis is the temperature. So for that case, we can assume the temperature is continuous variables, because we have so many almost infinite values measured by the thermometer. Okay, so that is the section 1.1. Okay, so section 1.2 is we give some example of simple summary statistics, such as sample mean. So everybody knows that already. So sample mean is we take a sample of size n sample. For example, we have 10 concrete blocks. The sample mean is simply calculated as this. So we add all the sample items value together and divide by the sample size n. For example, we have 10 concrete blocks. We measure the strength of these 10 blocks. So we add the strength for these 10 blocks together and divide by sample size 10. So that is sample mean. I think everybody knows that. Sample variance is called S square. Okay, so S is called the sample standard deviation. So S square is called sample variance. So it is calculated based on, one of these. You can use one of these two equations. Okay, so Xi is the sample items. This is the sample mean. N is the sample size. And the S is called sample standard deviation. So that is the square root of the sample variance. So sample standard deviation always be positive. Okay, larger or equal to 0. Okay, so cannot be negative. So that is the square root of sample variance. So sample variance is S squared. So the value of S is always positive. If all the sample items are exactly the same, then S could be 0. Okay, but cannot be smaller than 0, cannot be negative. So the larger the value of sample variance square, or S, again, S is called the sample standard deviation. Then the larger the variability of the data set. So if the difference between the sample, the measurement of the samples, the larger S. Okay. So in the previous equation, the sample variance is divided by n minus 1. Okay, so you may ask why it is divided by n minus 1, not divided by n. Okay, so here is the answer. Okay, so the sample standard deviation S often used to estimate the population standard deviation, sigma. Okay, so the sigma is the population standard deviation. For example, the 1,000 concrete blocks, the standard deviation of that is called population standard deviation. We get a sample of 10 concrete block. We calculate the standard deviation using the previous equation. We call that sample standard deviation S. Okay, so the idea is we try to estimate the population standard deviation sigma, use S, the sample standard deviation. And because sigma is a little bit larger than S, as a result, divide S by n minus 1 will better estimate sigma. Okay, so it might be seems confusing to you, but doesn't really matter. So remember how to use that equation and what is the difference between S and sigma. Okay. So let's get some example. Okay, so let's say we have 5 sample items, 1, 2, 3, 4, and 10. Okay, first of all, sample mean. The sample mean is all the sample items added together, divided by sample size 5. So the sample mean is 4. Okay. So the sample standard variance S squared using one of the 2 equations in the slides. Okay. So for example, the first sample item 1 minus the sample mean, which is 4 squared, plus 2 is the second sample item, 4 is the sample mean, and so on, divided by n minus 1. N is the sample size, which is 5, so minus 1. So we can calculate the sample variance, or we can use the other equation. Okay, the same answer. And then S is the square root of variance. So the sample standard deviation is 3.5. Okay, so very simple to calculate this information. Any questions so far? Okay. So more information about the mean value. So if we have a sample of x1, x2 to xn, and if y is another variables and yi is equal to a plus b times xi, here a and b are constant, then the sample mean of y will equal to a plus b times the sample mean of x. Okay, and similarly, we have a correlation between the sample standard deviation for y, this is sample variance, and the sample standard deviation for y as a function of sx. Okay. Outliers is another new definition. Probably we have heard about this before. Outliers are points that much larger or much smaller than the rest of the sample points. Okay. So when we see outliers, we should think carefully. Outlier may be due to data entry errors, okay, or they may be points that actually really different from the rest. Okay. When we have outlier, it may affect the sample mean and the standard deviation quite a lot. So we should not delete the outliers without thinking carefully. Okay. Sometimes we should calculate the mean value and the variance with and without outliers, and then compare the value. So for example, here we have a sample of 1, 2, 3, 4, 5, 6, 7, 8. So 8 sample items, and one of them is much larger than the remaining 7. So we call this outlier. Okay, much bigger. All it is much smaller. It is also belong to outlier. So we discussed how to calculate sample mean. Median is another measurement of the center of the sample. It is similar to mean, but not exactly the same. Okay. So to calculate the median, it is a little bit more complicated, but it's not too hard. First, we need to order the n data points from smallest to the largest. So we arrange the data set from small to large. And then look at sample size n. If n is an odd number, then the sample median will be the number in the position of n plus 1 divided by 2. Okay. If n is even number, the sample size is even number, then the sample median will be the average of the numbers in the position n over 2 and n over 2 plus 1. Okay. Seems complicated, but it's very easy. Let's look at an example. All right, we have a data set of 2, 4, 9, 8, 6, 5, 3. So totally we have 7 sample items. So first we arrange from small to large. So from small to large. And then we calculate. So n plus 1 divided by 2. Okay, sample size is 7. So we get fourth. Okay. So as a result, the median will be the fourth measurement. Okay. The first measurement will be here, 5. 1, 2, 3, 4. The fourth measurement will be 5. So that's the median. Okay. Very simple. If the set has even number, that's key in this case. So we have 6 sample items. Again, we sort it from small to large. And we also calculate 0.5 times n plus 1. In this case, we get 3.5. Okay. So what we do then, so we should take the average of the third sample items. The third sample item will be 5. And the fourth sample item, which is 6. Okay, so 5 plus 6 divided by 2 is 5.5. So that is average. That is the median for this case. Average of the third and the fourth measurement. So the median and the mean are similar, but not the same. In this example, we have totally 5 sample items, and one of them is outlier. The median will be the third sample item, which is here. But the mean value, which is the value of these 5 sample items added together and divided by 5, will be here. Because we have outlier here, the difference between the median and the mean are quite large, pretty big. If we do not have these outliers, then the median and the mean will be much closer to each other. All right, so another example. So we have a sample of 5. So 1, 2, 3, 4, and 10 So already sorted from small to large. The sample mean, so sample item add together divided by sample size 5. So the sample mean is 4. And then we calculate the median. So n is 5. So n plus 1 divided by 2 is 3. So the median will be the third sample item, which is 3 here. 3. So the median will be 3. The mean is 4. The mean is 4. Okay, so next we're gonna discuss quartile, but I don't think we can finish the quartile and the percentage. So I want to save it for the next class. So yeah, let's stop here. I will continue Wednesday this week. All right, so before we dismiss, any questions, general comments you have? I know, okay. So
Professor,
yeah,
I have a question.
Sure.
Do you post your slides on Lalima?
I think I did already. I can double check. So upload the slides and also the syllabus and also the guidance on how you can connect to the website, the publisher website.
Thank you.
Okay. All right. So nice to meet you guys. See you Wednesday. Bye.